Morning, everyone. Our first lecture is by Professor Sergei Dubovsky from NYU about confining strings.
Okay, good morning. So I will show the data very soon, but I wanted to start with a few more comments on what we were discussing last time at the very end, because this is an important point, and I didn't spell out everything clearly enough. So as I said, there are several situations where we know how to calculate finite volume. So, well, in one situation is in a massive theory. So we're calculating up to exponentially small corrections, and there is this below the multi-particle threshold. So one can use AB equations, which schematically look like this. Yeah. So basically, it says that you have particle in a circle, and the periodicity condition, so that's particle I, and there are many other particles, and the periodicity condition which you impose is affected by phase shift, which this particle experiences by interacting with many other particles. And basically, one of the points I was trying to make, that even if we are calculating these phase shifts perturbatively in effective field theory, it doesn't mean that it's a good idea to expand this equation in the phase shifts. And there are several situations where it's clear the case. For instance, and that will illustrate my comment, which I was trying to make about kind of quantum effects versus classical nonlinearities. So for instance, let's imagine a situation that all these particles are very soft, but there are many of them, right? So you have many particles on a circle. And in this situation, phase shift in each individual scattering is very small and well controlled by perturbative long energy effective theory. But still, the total phase shift which particle accumulates while interacting with many of them can be large. And clearly, in that situation, we don't want to expand this equation in delta, as kind of naive perturbation theory effectively is doing. Because we will be mostly interested in low-lying KK states where the total number of particles, like, well, actually, sometimes it's in some examples which I'll be showing, it will be on 4. So that's already not that small. But it's often still, it's kind of even when the number of particles actually is small, it may be a good idea to think in terms of that expansion, starting with thinking of state with large number of particles and then extrapolating result to small number of particles. Well, in another situation when its phase shift can be large is when you have a resonance, right? And that resonance may be light, and it's still kind of within effective field theory. But again, in that situation, you don't want to expand in the phase shift. And furthermore, it's related to kind of the first comment which I'm making here about the soft particles. So another ingredient in these calculations are so-called winding corrections. So, which are more important, at least naively, in this situation than for theory with a gap, because they're not exponentially suppressed. And so we need to worry more about them. And they are calculated, as I said, in the situation when in approximation, when the S matrix is integrable, they're calculated by so-called thermodynamic Bethe ansatz. I don't want to go into full details of kind of this technique, but let me give you an idea, and that will illustrate also the relevance of the comment I was making. The idea of this technique, so that kind of that we want to calculate finite volume energy on a circle of size R. And well, for simplicity, I'll be talking about just ground state, but for excited states, kind of there is some analytic continuation to be made. But the point I will be making is universal. And so for that purpose, one can consider a theory on a torus. So that's L, the extent. So in the initial physical setting of the question, this is a spatial circle. So this is space, and this is this is time, and so on. And then in the limit L going to infinity, the partition function on the torus, so L goes to infinity, it can be thought of as kind of, we already discussed, it can be thought of as being dominated by the ground state. So is 0 far, and this is what we're to calculate. But equivalently, you may think you can turn your head 90 degrees and think about this system as a system in the L to infinity. So if you think about this as space and this is time, then in the L to infinity limit, that becomes a thermal partition function on a space interval which goes to infinity. So the same quantity can be thought of as thermal partition function with a temperature which is given by inverse size of the circle, and so it's calculated, and this F is a free energy, thermal free energy at the temperature 1 over R. And then one proceeds calculating this free energy by looking at the interacting particles on a circle. And because it's in the infinite volume, or in the very large volume limit, so the density states of these particles, one calculates using ABA equation, because we're taking L to infinity limit. So effectively, in this calculation, there is a hidden like ABA calculation exactly with a large number of soft particles. And again, as we'll see momentarily in the examples, so that's leads to the fact that actually the binding corrections will be small, but as I will illustrate, that actually it's better not to calculate them at all than to calculate kind of by truncating that expansion of that equation. We'll see, but kind of in this calculation, it's hidden exactly this situation when you may have a large phase shift because due to a large number of particles, but which are actually soft, and so that you don't want to do just the most naive perturbative expansion. And finally, one last comment, which for many purposes it's a trick, but it captures most of in this situation, it captures most of kind of what we are doing, although it's not the full story yet, but maybe for some people it may maybe bring some comfort thinking about that way. Well, the trick kind of, let me call it TT bar undressing. So we can formulate this procedure in the following way. So there is the following story. So if I have two series, let me call one dressed one and another undressed one. And these are S matrices of this series. And for simplicity, I will be talking about massless series, which is the interest here, but there is a generalization of this formula for massive case. And so if I have the S matrices of this series, so there is some bunch of left movers and right movers here, bunch of left movers and right movers here. So if the S matrices of these two series are related by this factor, which is very simple in this case. So this PL and PR is the total left moving and right moving momentum of particles which are present in the collision. So the formula is slightly more complicated for massive theory, but it's still quite simple. So this is what's called, so kind of one says that this series, this dress theory, is TT bar deformation of undressed theory with this parameter. And like Igor was asking yesterday questions, there are this kind of some concerns about to what extent TT bar deformation UV complete, non-perturbatively well defined. Well, all these questions are mostly about definition of local offshore observables, and actually, similar to how, well, for massless bosons, TT bar deformation for 24 massless bosons, TT bar deformation is just equivalent to this ISS matrix which we discussed before, and we saw that it's gravitational theory. and actually all of these dress theories, if one starts with conventional quantum field theories, they will be gravitational. And actually, I don't think there are well-defined conventional local observables there, but well, it's a question under study, but it's from the point of the purpose of what we're doing, that's not important, because kind of this formula, that's exact formula. The level written on the S matrix is defined at all energies. And the statement is that what was shown by Zamalochikov and collaborators and by Tateo with collaborators, that if in this situation, there is a relation between finite volume energies of undressed and dressed series, well, which is governed basically, there is equation of this kind. dl squared En equal 1/2 En dr En plus Pn squared over R. We some kind of what this relation between S matrices, finite volume energies, there is in one-to-one correspondence with each other and related by this exact equation. And so it's our choice. Kind of we want to calculate finite volume spectrum of any of the series. We may, for say, of dress theory, then we may either start directly calculating in dress theory, or we may start calculating it undress theory, and then dress the result using this formula. So if you wish, it's a little bit like a choice of the mu parameter in usual perturbative calculations of regularization scheme, right, of the regularization scale. And so given that in the string context, at the leading order, the theory is given just by TT-bar deformation of free massless bosons, it makes sense to kind of undress that fact, which is the level of effective action corresponds to undress theory, which will be constructed with operators which don't have terms like dx to the 4, dx to the 6. So there are no just first derivative interactions. So work in the undress theory, calculate perturbatively in the undress theory, and then go exactly to get the answer in the theory which we care. Use this exact relation between finite volume spectrum here and here. So it's similar how we do in kind of like in RG calculations, right? So we want to calculate at one scale, we kind of do calculation perturbatively, but then we RG improve. But this improvement corresponds to the summing of some logs. So that's kind of one way to think about what most of what we're doing can be also thought about this way. Yes.
Ask about, so you said this very interesting thing yesterday that this tachyon is hearing some radius thing because there's the confinement.
Right.
And here the energy becomes
right. The ground state energy becomes imaginary, but really kind of this sector just disappears because so that theory just doesn't exist. That cannot be put in a circle smaller than R, because from the gauge theory perspective, that would be the confining phase, center symmetry is broken.
Maybe it's a silly question. On the lattice, if you go on the other side of the deconfining transition,
well, that the center symmetry.
Does E go like 1 over R?
No, but because remember, we're simulating not directly the flux tube theory.
Just on the lattice side, what happens?
The center symmetry is spontaneously broken. So this two-point function, of two Wilson loops, which we're calculating, doesn't measure for us finite volume spectrum of a Wolf-Sheet theory anymore, because there is mixing between closed loops and the center symmetry. There's no selection rule anymore. So really just these observables which we are measuring in that regime cannot be interpreted as their finite volume spectrum of the Wolf-Sheet theory.
Right, but what do you see like if you just look at
well, the Wilson loop now has an expectation value, right? So we need to subtract.
So you have to subtract.
Right, yeah, so. Okay, so yeah, I know. Are there any further questions on that? Because I'm about now to show slides which illustrate some of these points. But actually, I would like to emphasize, so clearly this is incomplete picture. And in particular, when we're approaching the situation now where on the lattice, like Mike with Andreas, they provide measurements of many multi-particle states where, and at the precision kind of they're working now, the effects which break integrability, they're becoming important. And clearly, kind of to extract information from the data, we need more work. We need to understand better how to make this transition between finite volume energies and kind of extract from the information about this theory. So that's a very concrete question, which I think quite interesting and very rich. And this is one, I think, one of the questions where we can definitely make progress in this collaboration. And it will be important not only for this, but also that's a classic question also in general in lattice quantum lattice quantum field theory. And that's the theoretical part which is built in there, how to go from finite volume energies to scattering. So clearly that's not the final answer, but there's something can be. Yeah.
So the transition you are describing there is essentially Attic-Witten type of transition, right? The mode becoming tachyonic, but in principle, you know, if you are at large n, if you stabilize the center symmetry, right, and continue to small l, you will remain in the volume independence regime where this Iguchi-Kawai works.
Yes.
At least there's a general principle, even from small l. But if you are at strictly unequal, it's sufficiently large n, it should be possible to get some spectral data.
But it's not literally in the theory, because you need some to deform the theory, right?
Deformation, you know, its impact on the theory, for example, on pure Yang-Mills, on spectral observable is order 1 over n squared.
Yeah, maybe we should discuss it more. But for instance, one situation where something like that happens is that if one introduces fermions in the theory, in this TT-bar deformation story, if one adds fermions, and if one, because actually this TBA trick, it most directly relates in the presence of fermions. It's mostly directly relates not the thermal partition function, but the twisted partition function, because you want to impose, if you impose periodic boundary condition in this direction, that it also be periodic boundary condition for fermions in that direction. And so in that situation, if there are more fermions than bosons, then actually this singularity doesn't occur in this calculation. And that matches very well this, I think, what happens in your story, that basically by adding even very heavy fermions, because what one cares is about deep UV behavior of densities. So that by adding very heavy fermions and looking at the twisted partition functions, one avoids the center symmetry break-in transition. So this very nicely matches what happens here. Okay, good. So yeah, if there are no more questions about this, let me finally now show you data, and which will hopefully illustrate some of the points which I was making here. So all data which I will be showing is from papers of Mike and Andreas over several years, and I think so maybe even earlier data where also Barak Bringles was involved. So this is the ground state energy. That's the simplest situation. And so, well, here the two slides. This is the full energy. And kind of that's shown to illustrate that we talk about a string. So it on the horizontal axis, there is the size of the compact circle. On the vertical axis, there is energy. And here I'm showing full energy. But in the remaining slides, I will be always showing energy with subtracted linearly growing piece, so that we can see details of what's going on. And that's what's done here. And here the well, there is data points, and well, actually there is more precise data now, but that's good enough to illustrate the points I'm making. And the theoretical curves here, these are some of universal terms in a less over expansion. So this is a situation where there are no these subtleties. You just do one over expansion. There are, as we discussed yesterday, there are first universal terms. There are 5 of them. And then non-universal term starts, and one can see up to very small strings. So here the size of the compact circle is measured in the units of LS, up to the very small strings. So somewhere here that's where phase transition happens. I don't remember it exactly, but it's for this theory, but it's very close to this point. But up to very small strings, which don't look like long strings at all. It's more like large blobs. This sum of universal terms, it really describes very well the data. Well, in particular, this first term here, which is what's called Lusher term. So the coefficient here would change if that's really just free field Casimir energy. So coefficient here would change if there were additional massless states on the string volt sheet. And this data completely very unambiguously shows that there is no room for additional massless states. But also, well, it's nice. We see that simulation works, theory works, but it really tells us that it's very hard to extract any information. If our goal is kind of to do experimental physics here and to extract information from lattice data about volt sheet theory, it's very hard to do it by looking at the ground state. I think the good analogy is kind of in particle physics, there is kind of low energy frontier and like precision frontier. That's kind of what we're doing here when you something like measuring G-2 and trying to figure out physics at the high scale, and building colliders when we collide real particles and see what happens. And if we have enough resources to bigger collider, that's usually more direct and more easy tool to understand the physics at high energy. So that's similar situation. That's like doing low energy kind of high precision measurements. And here it's kind of that universal terms from that viewpoint, it's really like standard model background, something which is just if we can calculate, we know it should be there. It's nice to check that it matches the data, but it's not what we're interested in. So, okay, so that's illustrates this point about ground state. And the next slide, this set of states was very revealing as far as all these discussions which we had before are concerned. So what's shown here? So here the green line, that's the ground state with subtracted linearly growing piece. And these other states, these are excited states which have left movers only. So if you think about collider, they're still very boring states, right? This state is the first KK excitation with 1 unit of momenta. So that there are just one left moving phonon propagating. And this state is one of the n equal 2 states. But again, they're just, yeah, actually, I don't remember which one I showed here. As it was unit 2 but it's one of those states. There is either 1 or 2 phonon propagating here. But yeah, what the lines show is the following. So the solid line, just like before, that's the result of this. That's the sum of universal term. That's honest kind of calculation in LS over expansion. Now the dotted and dashed lines, dotted line, this is just the free theory result, which is equivalent in this case to using ABA, because there is nothing, no particles to collide, so there is only left movers moving. So ABA would give the dotted point, and kind of one sees that this data point is, well, it's kind of very close just to free theory answer, and one is not surprised about that because you just have a left mover. Well, and the dashed line, that's the full TBA calculation for this state. So it includes binding corrections. One sees that they produce an effect, and actually it goes in the right direction. But it's a small effect. But for small string scale, so here one is not that worried because these are really short strings. So the naive perturbative expansion actually works pretty well up to this R over less of order 3 maybe, but still there was this kind of a surprise why and at the same time, yeah, these dashed lines, which is from the point of view of technique which I'm describing now, that's kind of the calculation with TBA calculation with leading node S matrix. That's also what you get by doing naive light cone quantization of a string, and that was something which was puzzling people. So why, even for very short strings, why the kind of naive quantization, which we know is not correct, why it produces much better agreement with the data than apparently correct perturbative calculation. But I think it illustrates this point that kind of as far as binding corrections are concerned, so it's definitely better not just not to calculate them, they're small effect. It's better just not to calculate them rather than to truncate this expansion in the ABA, which is used in TBA for winding corrections. So kind of this solid line, what it does is this truncated expansion, it just really screws up at short distances. So, but these states are still, they're not very useful because, well, nothing kind of from this ideology that what kind of we're looking at the collider and we want to probe physics at high scales. We're not colliding anything here. We just.
What are the three curves?
So the three curves, solid curve is a sum of universal terms. These three curves. This is the ground state. This is KK momentum 1, and this is KK momentum 2 for left movers. Okay, good. So this is kind of in the collider analogy. It's like you just turn on the beam and you check the property of your beam, but you're not colliding particles here. So now let's look at the really interesting states where you start colliding particles. So here, these are the states with one left mover and one right mover. And as you heard from Zhao yesterday, when in D equal 2, well, there are three channels, which in D equal 2, that corresponds to symmetric, antisymmetric, and well, antisymmetric, which with respect to D minus 2 is the same as pseudoscalar. And symmetric is a spin 2. There are two polarizations there. These are Green's lines, and the scalar. So these different colors, they correspond to different channels. Well, so these green states, and that's a bit annoying. So in the continuum, they're supposed to be degenerate, but so these two sets of green points, they show the two polarizations of spin 2, which are supposed to be degenerate in the continuum, and that splitting is a lattice effect for the reasons which I don't quite understand. Somehow Mike says that it would be incorrect to judge in general the level of lattice uncertainty from splittings between these two states, because it would be much larger than error bars on other points. But for some reason, kind of splittings between these two spin states is larger than the typical discretization effect for larger states. But that's definitely, kind of talking to our lattice friends, definitely that's something which one would like to improve and would like to see convergence between these two spin states closer to each other. And we'll see momentarily that's quite important. But so what's shown here is so the green and blue line, that's the result of summing, again, universal corrections in 1/r expansion. So there are only two colors here because at the level of universal corrections, there is no splitting between scalar and pseudoscalar. So pseudoscalar would be predicted to be degenerate, exactly degenerate with the scalar. And dashed line instead, which works kind of much better, at least for scalar and symmetric tensor, that's the light quantization, which would predict all of the states to be degenerate. So that would be common prediction for all three states, and works better for two of them. And universal corrections in this case, they include this effect, this order, they include this 2-2 scattering, which introduces annihilations, and that leads to the splittings between spin 2 and the scalar and pseudoscalar states. So that situation was kind of, if one just looks at the LS over expansion, and actually here it's, well, basically in all regime where there is data, it's kind of clear that this expansion doesn't provide useful guidance. And if anything, people will say, oh, maybe it works kind of for these 2 points, but anyway, so let's now see what changes if we apply this TBA technique. And the result is this one. So instead of those two lines which I was showing before, now it's still at this order because I'm using the same input. The fact that blue and red are degenerate, that remains correct. But so here, this dashed line, that's light cone. That means you calculate this matrix at 3 level. In the language I was using before, if you calculate this matrix at 3 level and go exactly from that S matrix to finite volume spectrum. So this green and blue-red curve now, I calculate S matrix including one loop correction with this annihilation term, and then again go exactly to finite volume spectrum, and that's what one finds. Well, and so here it's kind of, it makes sense. So first of all, the splittings between these two curves, it's of order, it goes in the right direction, and it's of order the splittings between blue and green. And it kind of becomes clear that it's pseudo-scalar points. These are clear outliers. So it seems hopeless to explain these points by some higher order effects, for instance. But on the other hand, there is a very clear feature of these red points, namely, so here we're measuring the mass gap, right? And you see that the mass gap in the energy gap in the pseudo-scalar channel is it's roughly independent of the size of a spatial circle. So it looks as if in our theory we have additional massive particle, and we added this at rest, the massive particle which is pseudo-scalar. So that's how this picture looks like. And so yeah, that's then the next step. Well, that's kind of what this slide is saying. How do I? Yeah, let me try to go full screen. Hope it won't unfreeze. So motivated by this data, that's then what we did, right? So kind of that looked as a discovery of massive particle in this one-dimensional collider. And so we added these massive particles and two new parameters here, where the mass of a particle and the leading order coupling. It's a pseudoscalar because it appears in the pseudoscalar channel. So that's the leading order coupling, because K is their extrinsic curvature of the Wall sheet, and this leading order operator, leading order pseudoscalar operator, which one may write, it happens to be for strings in 4 dimensions, actually happens to be a topological density. It counts so if you have 2-dimensional surface in 4 dimensions, that in generic configuration, it will self-intersect over a discrete set of points, and you count the number of these points with signs dictated by orientation. So this density here, that would be the density, topological density, which counts that topological invariant. And so for these reasons, we call this kind of particle Wall sheet axion, because its leading coupling looks like coupling to some kind of FF dual thing. And so we have two new parameters, mass and this coupling constant. And so the mass, so yeah, and then we introduce this particle, it produces, like we calculate now S matrix, including the exchange of this particle that leads to resonance in the S channel. And the mass can be more or less determined by I, by just kind of, it's a little bit better, there are winding corrections here included in TBA calculation, but morally you may determine it by I, just looking at the height of these curves, curve that fixes the mass. And this parameter, this coupling constant Q, it's determined by splittings, by how it affects, because this particle also in the S channel, it produces a resonance in the pseudoscalar exchange, but in the T channel, it affects splittings in the between a scalar and spin 2 states, and that's kind of where what allows to determine the value of this Q parameter. And so here different lines as a following. So dotted line, that was just what we had without adding this particle at all, and solid or dashed line, because there are clearly discrepancy between these two sets of spin 2 states. So we used either to fit either one of them or the other, and kind of use that uncertainty as one way to estimate. So that's actually the main source of this uncertainty, this kind of roughly 10% error bar on this coupling constant. It mostly comes from the splitting between different polarization in spin 2 states. And as I said, it would be very good if our lattice friends could shrink this splitting, because I will talk more about that. But already now I can say that kind of when Zhao was showing the parameters of his resonance on which lies right on the boundary of bootstrap region, and so these were exactly those points were determined by this mass and this coupling. So these values within error bars, they exactly coincide with the boundary of the allowed bootstrap region, what one finds on the boundary of bootstrap region, and what Zhao was showing you in his lecture. In physical units, the mass of this particle is like 750 MeV. Well, these are, yeah, good. So I'll maybe show the next slide, but basically, first of all, one should one can see error bars here. They grow as one goes to longer strings, just because one measures exponentially decaying correlator, and the longer the string, the heavier the corresponding energy. So this exponent becomes very hard. So it's hard to measure the long string. So there are large error bars here, and around this place. So here I'm showing only the ground state in this channel, but there is first excited state, which I'll probably show very soon. And later today, one of the participants talk will be Song-Han Luo, who show more of this data. So here there is excited state, and around that place there is a kind of avoided crossing level between those states. And so there are kind of, and then it becomes also a bit tricky to correctly measure the individual energy. So the kind of short answer that kind of I think it's really just uncertainty. And there are reasons why it's hard to measure energies in that region. So did it? No, it's not for some reason. It doesn't. Yeah. Okay. So I'll do it this way. Yeah. So that's kind of what I was trying to illustrate. So this is. So I was showing all the data. This is in new data, new unpublished data by Mike and Andreas. And here I'm showing just first excited and says like ground state, that's resonance, and the first excited state in the same channel. And so first one sees here that error bars shrank quite a bit, but still this is a tricky region because here the states approach close to each other, and probably they're still kind of not well separated in the lattice measurement. But what was being done here, it's illustration of the kind of second way of thinking about lattice data. So here, well, this solid feed, this solid curve is not really, shouldn't be thought of a theoretical prediction, but rather kind of, I think what Song-Han used here is, well, there is a, for S matrix, well, there is leading order result, which we have, but then parameterized some higher order powers, because these states, they correspond to quite high momenta, and one doesn't expect effective field theory to break down here. So basically what one attempts to do here by using this set of TBA equations to go to experimentally determine going from finite volume value and just measure the phase shift in this channel directly. And that's what also lattice people that trying to do this also say for pi and scattering can see resonance in this way. So, and again, there are some caveats to what is being done here because we're approaching high energy. So we're neglecting say 2 to 4 scattering. So well, it should be taken with some grain of salt, but still kind of again, there are some points which clearly have large error bars and outliers, but one see kind of a nice resonance curve, and then afterwards phase shift flattens, but then it looks like it starts growing. But definitely we would like, so that illustrates the point that there is quite a bit of lattice data, and we want to be able to extract information from there with better confidence. No, dotted, actually, Song-Han, do you remember what dotted? Yeah. So, right, that would just take this extra particle and calculate, they do the same S matrix, which we used before, but don't introduce any other higher corrections. So basically that would be kind of theoretical prediction of low energy effective field theory. So yeah, this dotted line illustrates that really this whole curve here is really shouldn't be thought of as theoretical prediction. It's more, again, I think the correct way to think about what's being done here is really we're trying to measure phase shift from lattice data. So yes. So clearly effective field theory doesn't work that well for these states, but one is not surprised because, well, these states, as you can see here, yeah, so another kind of advantage of this TBA method that it tells us when really we don't expect, when we expect the effective field theory to break down. It's not necessarily when circle size becomes small, because excited string kind of its physical length can be quite long, right? So we have very long and smooth string wound around small circle. So really Lorentz effective field theory breaks down when the momenta of particles which you have in a string is large. Well, and here we see that we're talking about particles like for this point, they correspond for momenta like between 1.5 and 2.5 in string units. So one is not surprised that Lorentz effective field theory breaks down here. But really, that's what we want to do with more confidence. We want to be able to go from finite volume data to extract information about phase shifts kind of without doing perturbative calculations. But no, solid curve is a fit corresponding to this phase shift, which is drawn here. So here, we use TBA equations to extract kind of basically to extract these points, and one fits these points with this phase shift, and then goes from this phase shift. But yeah, there is not much information in the solid curve, right? So probably, yeah, it's the same thing happens. Okay, so that's the data which I wanted to show for the Young-Mills. Well, there are more states, but kind of, and you'll hear a bit more from Son Han today, actually with new data. There are more different other channels. But the summary here that all existing data so far, it's consistent with just one additional particle which appears in the this pseudoscalar channel, and it goes up to pretty high momenta in other channels. So in other channels, there is no sign of any additional massive modes. So now this is the data for 3D Young-Mills. So there it's simpler. So again, this I'm not showing ground state. These are excited states, so it's simpler because there are no different channels. There is only one Goldstone boson. So well, again, as you heard already from Zhao, so you know that story very well. So what's shown on the left-hand side, these are two and 4 particle states, and here so this is this is state with one left mover and one right mover, and these are states. These are a pair of states with one left mover and right mover with double KK momentum, and 4 particle states with single KK momentum. And so the dashed line here, that's a light cone result, which again leading order calculation using this TBA technique, and it kind of works and it predicts exact degeneracy here. But now that's maybe the cleanest sign. So if one looks at the 2 to 4 this excited states, one clearly see that even for long strings, there is a splitting between 2 and 4 particle states. And that's the signature of breaking integrability. That tells us that the phase shift which we see here is not just pure e to the s, but that there are corrections. And now what one can do, and also here, kind of we see that the shorter strings, there is a deviation from the predictions of light cone quantized series. So we can do kind of, can play several games. One can do some cut again, like either introduce higher order operating effective field theory, this gamma 3, which K to the 4 operator, which Zhao talked about, and calculate prediction using that by cutting data to the points where momenta are small enough so that one can still contrast effective field theory. Or one can also introduce some higher order corrections as a judicial parameters and kind of extract the phase shift. So we played several games like this, and they all look pretty consistent. So let me show the result which one gets. So yeah, so this is analogous plot to what I've shown in the resonance. So it's extraction of phase shift from this data. And so while there is always outliers, so these outliers, they correspond to, on the previous plot, they correspond to kind of this shortest state. So clearly, well, here one pretty close to the phase transition. And so clearly we kind of don't capture what's going on there, but we're not these are really very, very short strings now. We're not all that worried about those. But apart from that, so these points, they kind of nicely seem to follow a certain curve, and kind of also one sees some consistency here. So you see there are these violet lines and the blue lines, which correspond to different levels. So these violet lines, these are the shortest lines, they kind of shortest lines, shortest points here, and this blue instead, these are the KK excitations with momentum 2 at larger radius. And so, yes. Well, that's, well, we know basically kind of, we look at the first level and we see that the energy at short distances is smaller than 4 to the s. From that, we know the sign of gamma, and we say, oh, we attribute it to the changes of phase shift. So we know that determines the sign of gamma 3. And then kind of, so we don't know directly from the lattice. We theoretically assign it based on this knowledge. Yes.
So to get energies of two states with the same conserved charges, you say the 2-point function to a sum of exponentials?
Well, the way people do it on a lattice, they don't measure just single 2-point functions. They construct large bases of operators and look at the correlation matrix. And then they try to essentially construct approximate wave functions in this truncated state. So they really try to construct many approximate eigenfunctions in the truncated space. So they don't look at single wave functions. There are single correlators. There is large correlation matrix they're studying. Right. Yeah, so this coming back to what Java was asking, this is kind of being this labeling what is 2-particle and 4-particle, that's being theoretically. So basically this blue should, because we see here that the correction from the phase shift is such that the energy becomes smaller in high momenta. And that's why we say, oh, this out of these states, two states with KK momentum 2, they have larger momenta. Hence, that should be blue states, and green states, they are softer and they're closer to the light cone prediction. So that's how we do this determination. And then this curve again, there is a so here different lines show the following. So the dashed line, that's the just leading order phase shift, light cone prediction. So the solid line, this is the light cone plus gamma 3. So it's a single power law correction, and you see that it works for quite a kind of, we determine the size of this correction from this part of the spectrum. But then we see that actually at even higher momenta, clearly there is again a significant deviation from that. And this red curve is just, again, it's kind of phenomenological feat with introduction a couple of extra powers. But really one should think about kind of, well, one shouldn't take the curve here is not meaningful, but looking at this region, one kind of see indication that maybe kind of there is intermediate region where phase shift deviates from e to the s, but it looks like maybe it wants to come back at high energies. But definitely it would be interesting to measure this more, but that's kind of the lesson from. No, they just correspond. These are, well, essentially, yeah, you can see this effect here, right? It's this set of points. You can see that at larger R, so these are KK states with double momenta. Well, and actually, this is here I show it's just a subset of data, and these blue points, there are much more of them because I use better data there. So these blue points are for relatively short strings, but not too short. So actually, they're very reliable on the lattice, and there is a clear sign here that somehow these splittings between 2 and 4 particle states, it looks like it's shorter for shorter strings. It tends to shrink down. That's the effect which you see on the phase shifts, that at first it deviates, but then it looks like it goes back to light cone prediction. And yeah, these points, well, and again, there is better measurements which I didn't include here, but which I included on that plot. Yeah, so like these points are clearly like this drop off down there, that we're clearly not trying to explain. And well, one should think about what it means, but clearly that's not something where it's present essentially in all states. The shortest point close to the phase transition, they show this behavior. But we're not including those, and those, this again here, they correspond to kind of these points, which clearly one can see is already here. So there are these 2 points, the shortest points in the violet region, which clear outlier. But then one looks at the same range of momenta in another state and can see nothing really happens in the phase shift. So clearly, this is not something which has to do with the bullshit dynamics, but with phase transition or something like that. But points in this region, you see there are quite a few of them and with rather small error bars. Those look pretty reliable. And so, yeah, this effect that the splittings seems to get smaller as one goes to high momenta or shorter strings, it seems to be real here. Okay, good. So, well, just to and the kind of again bottom line here that well there are more states, but in D equals 3, there is no sign of any additional massive modes. So we see the phase shift is different, but there is no sign of resonance. And I'm not showing you all of the data, but and just to contrast it, let me show also some data, which this is data for K strings. So one can play the same game, but considering Polyakov loop not in the fundamental representation, but in some high representation, and that will create a string in different representation and with higher anality. And so at large n, morally one may think about them as kind of some bound states of several fundamental strings, and one expect in this cases for these bound states, one expects to see some breathing modes, some resonances, and that's I have a couple of slides illustrating that. That's for I think it's SU6. I don't remember. I think it's SU6, and this is a rank 3 antisymmetric representation. So one finds very nice resonance there, and also this is rank 2 antisymmetric representation again. But well, also you can see that the data, the finite volume data looks quite messy. But when you're using this TBA technique, when you map it to the phase shift plot, well, again, there are some outliers, but one kind of gets a reasonable phase shift curve here. And so in the places where we kind of expect to find these scalar resonances, that illustrates that we see them and see this phase shift. So the fact that one doesn't see any scalar mode in D equals 3 and Mills, well, and also D equals 4, there is a pseudoscalar. It looks quite significant. Okay, so as I promised, there will be kind of theory, experiment, and theory in my lectures. So we finally finished the experiment part. I'm coming back to conclude, make some theoretical comments. But if there are further questions about the slides, let me. It's a good moment to ask them. Okay, can we lift the screen, please? Okay, good. So, kind of the short summary of this experimental results, which I was presenting for you, that for D equals 3 and Mills, it looks like at least all what we saw so far is consistent with having a single particle in the spectrum, the Goldstone boson, and its phase shift starts as it should, as e to the s at low energies, then there is e to the s cube correction, but kind of there is maybe some tendency that actually, well, that plot we show that it comes back, but well, that's definitely something which should be studied more. Now in D equal 4, so we have x1, x2, and then we have this pseudoscalar axion, and we have which has a mass and q, there is mass and q. Take these values. So now it turns out there is something interesting about kind of this matter content, which actually makes it. And there is a way to think about both of these matter content in one unified language. So for that, well, we should come back to what we're doing in the beginning, right? We're asking this question, well, what is special about d equal 26? And we saw, well, what's special at d not equal to 3, but at larger d. What was special is that this universal one loop particle production which appears on the voltsheet. So it is an anomaly, of course. It's kind of what's called Virasoro anomaly, but formulated in from somewhat different perspective in a different background. And at least in this setting, it appears as an anomaly in this classical symmetry, which is responsible for integrability of classical Namu-Gotter. And so just like for any other anomaly, it's maybe natural to ask, okay, what it takes to cancel this anomaly? At least to me, that looked like a natural question. So, and clearly to cancel the anomaly, because it's calculable IR effect, we need to add some extra massless particles, right? To cancel this effect. And so the first thing which comes to mind, so the first thing which comes to mind, let's add a scalar. Let's add additional. So let's work it. So now I'm at d equal 4, not at d equal 26. Let's add additional massless scalar. So we had these Goldstone diagrams which roughly behave like this, and well, this more particles which lead to this anomalous scattering. So let's add a scalar, additional massless scalar, and try to tune its coupling in such a way that it would be canceling these diagrams. And well, the leading coupling. So when you add this scalar on the voltsheet, well, there will be interaction like that here. H is there. Induced matrix, so I still work in this in this static gauge formalism. So I'm not using Polyakov formalism, but I need to write interaction in this form to preserve nonlinearized Lorentz symmetry. And the leading operator, which one may write here, it will be this operator, d2 sigma phi r, where r is a curvature constructed out of this induced metric. And then actually, indeed, one can check that there is value of q. One can find the value of q such that it will cancel this particle production at one loop. And last time I sketched for you the argument how at d equals 3 we had this ugly inductive argument which shows that e to the s can be promoted to. But it's really, there is a Poincare invariant theory which exists to all orders in derivative expansion which reproduces to e to the s. So this argument works also in this case. So there is also a proof that now we have 3 particles, x1, x2, and let's call it phi. And there is an integrable theory with the same S matrix, e to the s, ls squared over 4. Which would be now integrable and Poincare invariant and describe the system of particles. Now, of course, what I'm telling you here, it's a very complicated and convoluted way to say something which string theorists know very well. That just, if I reformulate it in the standard Polyakov language, this is just a linear dilaton theory. Kind of that was, but it's a nice check that this method relying looking at integrability for long string. Applying this method, you can reconstruct something which we know is there. So this is a linear dilaton background, and that's kind of from this viewpoint, that's another way. That's one way to cancel this anomaly. Okay, now, well, we know that's kind of it doesn't look like QCD takes anything like this route. But following this logic, one may say, okay, let's add instead, let's add a pseudoscalar particle on the voltsheet. And the story is goes exactly the same. So the difference is that now the leading operator is the one which you saw before. So there is a k tilde. And from the viewpoint of this calculation, from viewpoint of looking for integrable model on the Volt sheet, it looks very similar. Just you're using different operator. It's a particle with different quantum numbers, but the whole construction looks completely identical. And you find that there is also an integrable model with this particle content, with 2 Goldstone bosons and one pseudoscalar, which would be integrable if you have additional massless particles, massless particle. And integrability, moral of integrability fixes the value of Q. So because this diagram is supposed to cancel this one, you fix the value of Q. It's something like square root of 7/16 pi. So it predicts what should be the value of Q. Now, comparing to what we have there, the surprise turns out to be, of course, there the axion is massive. It's not massless. But then it turns out that the value of Q, which was determined from lattice data, it actually, again, within error bars, which was this 10% error bar which I had there. So this is, I think it's something like 0.37 or something like that. So it actually works numerically, it works better, but still we have quite a bit of error bars there coming from the fact that there are these 2 different states. So this value of Q, it agrees with this value, which one finds out in this exercise. Well, I should say that for this theory, unlike for the scalar theory, we don't know alternative formulation. We don't know analog of kind of Polakov formalism, because this particle is coupled to extrinsic curvature. So there is no useful way to, like, at least we don't know, and that's one of the challenges, that there is, we don't have a useful way to rewrite this theory in the kind of standard formalism, which would make it more tractable. But as far as we can tell, this theory exists, and there is this numerical coincidence that the coupling constant which one finds in this theory looks like the one which is determined for the axion on the lattice. So kind of then one can summarize. So both what happens in d equals 3 and d equals 4 can be summarized in the same way. So in both cases, we find a particle content of a potential integrable model, but it looks to be deformed. So in one case, there is this deviation from the phase shift, which appears at scales of order string tension. But there is some indication that if one goes to high energies, that actually this deviation may go down. And also here, we have a particle content, again, of potential integrable model, but integrability is broken because the particle is massive. But okay, QCD is full of 10% coincidences. And so one should be careful with this numerology. But so either you think that kind of this coincidence is complete numerology, or the question is, how would one try to explain it? How would one try to make sense of it? And the only way to make sense of it, which I see, is to say that, well, maybe this violation of integrability in QCD, that's kind of that's transient phenomenon, which exists at energies of order lambda QCD. But when one goes to high energies, then the theory, at least for some kind of improperly defined sense, becomes again approximately integrable. So if you go to high energies, this kind of mass can be neglected, and the theory looks like it wants to become that integrable model. So that's the only kind of scenario which I see. Now let me conclude by saying that, well, it's a posteriori. Well, actually, that doesn't sound that crazy. So if one thinks about kind of intuition of what's going on from gauge theory side. So both this particle content, which we find at d equals 3 and d equals 4, and kind of this statement about at least approximate integrability, I think there is some intuitive reasons to expect that to be the case. Although, again, that was cooked up a posteriori. So you shouldn't take it too seriously. Yeah, right. Yeah, yeah. Well, I don't think well, it's somewhat analogous, but yeah, I think that's the proper analogy. You cancel in loop effect against some tree level exchange, right? Right. So remember here, kind of coming back to my first lecture. So we're trying to think about bullshit theory in the regime of energies. This one, right? So 1 over less, which is the same as lambda QCD, and much smaller than n times lambda QCD. So that's what latency parameter told us. But these are high energies, right? So kind of you expect that some intuition. So we should be able to get some insight from perturbative QCD about what happens in this regime, because we know degrees of freedom of QCD at high energies. And indeed, you may think about interior of the confining string instead of thinking about it as infinitely long. Let's think about it that way. We introduced some QQ bar pair of heavy quarks, and we separated them very far apart. That's another way to set up long string. And so what we are studying here, we're studying kind of interior of a heavy quark meson, and we're asking ourselves, and what are high energy at high energies? What are the degrees of freedom which we see there? Well, we expect kind of from perturbative QCD, we kind of know the answer. We expect to see partons, right? And because this is pure and Mills, so we expect to see gluons. And indeed, this beta content, kind of what the operator which creates a string, it's in this one. So that string goes, let's call this z direction. Then to create kind of elementary excitation here, what you can insert powers of f here. That's the only adjoint which we have in this theory. So that would correspond to kind of inserting gluons inside this line. And in case of 3 dimensions, so we can only insert, like, what, let's call it x, the remaining directions, remaining spatial direction. We have only this operator to insert, which in lattice language, as I was explaining, answering Ed's question. So what lattice people really do, they construct a large basis of operators and look at the matrix of these operators of 2-point functions, and kind of the operator, which roughly speaking corresponding to creating a gallstone on a string bullshit, that corresponds to attaching plaquette in this direction, right? That's that corresponds to this picture, and that's the state which we find in D equals 3. So just by quantum numbers, this is the gallstone boson. Now that's in D equals 3. In D equals 4, one can insert FZX, FZY, and these operators match quantum numbers of the gallstone bosons. They're protected and they're massless. But in addition, there is also this operator. You can insert plaquette kind of, which goes in the transverse plane, and that's what has quantum numbers of the axion, which I was talking about. So kind of from this perturbative viewpoint, this axion it's really gluon. It's kind of additional, if you want, it's additional polarization of gluon, which appeared because this gluon now is inserted inside the string. So it's created by, but I think it is a gluon. Well, there is nothing else in Yang-Mills at high energies. So from that point of view, it actually would be somewhat surprising to find something else. But also this story about, at least in some sense, approximate integrability, also somewhat natural in this language, because what are we doing? We're taking kind of two of these partons, studying high energy scattering. So we're taking two of these partons at very high energies and asking what happens when they collide. Well, so as they approach each other, with large center of mass. So due to asymptotic freedom, not much happens as they go through each other. But I work in the infinite n limit. So I took this finite limit when I first took NC to infinity. So they go through each other, but string doesn't break, right? String doesn't break, and so they went through each other. They keep going. And they kind of form zigzag configuration, like long zigzag, but then they bounce back when eventually the zigzag becomes very long. And that gives rise to time deal, and they come back, right? So that's, again, being very naive of what asymptotic freedom means. That's the picture you would draw for how high energy scattering on the string volt should look at high energies. And actually, in this story, you expect so first of all, because it's high energy and asymptotic freedom, there is no hard particle production. When they go through each other, basically you don't produce any hard modes. You don't expect theory really to become integrable. Actually, you expect quite, at least naively, I expect quite a few of soft particle production during this long period when the zigzag is being formed and these particles are moving. So one should be careful what one means by the approximate integrability. But at least kind of one expects that, so for some properly defined subset of observables, one wouldn't be surprised to find that in some sense there is approximate integrability here. So that's kind of an intuition which I have, which again was cooked up a posteriori, so you should be careful, but that intuition which I have to kind of justify this picture that the violation of integrability can be a transient phenomenon which present at the scale of the lambda QCD, but disappears at high energies. And coming back to the question, which was kind of implicitly asked several points already. So what are we doing here? What is the hope for us, right? So we know theory is not solvable. So, well, there are two possible directions. One, it would be very interesting to find a confining theory where integrable dynamics is integrable, is where confined Walsh dynamics is integrable, or to prove no go, that's impossible. And this one class of theories which one may look at maybe is to start in 2D, adjoint like QCD theories in 2D of the type, for instance, which Jomi was discussing in his lectures. And maybe among those models, that looks like a natural place to look. But as far as actual Young-Mills is concerned, I think, in my view, the best hope is really that try to kind of estimate, understand better this integrable approximation which emerged from this lattice study of the lattice data, and try to kind of develop some kind of perturbation theory, basically a combination of some low energy, but also do some kind of high energy expansion, which is very natural in QCD because it's asymptotically free theory, which would be expanding around this integrable approximation. So yeah, I should stop here, but yeah, please ask questions.
So given this microscopic picture of the worldsheet axioms coming from like stitching a plaquette, does that mean I shouldn't think of it as like a compact scalar on the worldsheet?
That's a very good question. I think, well, it is probably compact scalar, at least. Well, the closely related question is the following. So kind of, I said, well, we have this d equal 4 in d equals 3 story. In one case, in both cases, one finds an integrable bundle, which approximately, as far as meta content is concerned. The natural question to ask, well, whether such a model exists in higher dimensions? Because we don't know at least whether there are any confining series in high dimensions, but still one may ask this question about this mechanism for cancellation of particle production. And we don't know the full answer whether such model exists or not. But the statement, but at least at one loop, one can cancel particle production in a similar way. And the statement is, which we derived with Jack Donahue, which is sitting somewhere here, is that if such a theory exists at high dimensions, then in general D, the model would be the following. So what you add, you have Goldstone bosons. So you're considering long string. You have Goldstone bosons. And what you need to add OD minus 2 WZW. So which basically this OD minus 2 that corresponds to kind of transverse rotations around the string. So from that point of view, and that kind of degenerates at d equals 4 and d equals 3. At d equals 4, you're left just with a pseudo scalar. But it's from that perspective, it's natural to think about it as being compact. And d equals 3, well, there is nothing left essentially, but still kind of it's tempting at least to think these two theories actually being members of the same family of models. But we don't know. So kind of whether such integrable theory exists in larger dimensions, that we don't know.
Yeah, I'm a bit confused about the argument of no, no particle production at high energy. I thought at high energy we expect lots of particle production.
Well, we expect of lots of soft particle production.
But the soft particles are still particles.
Yeah, but that's what I mean, that one should be careful what one means by approximate integrability at high energy. So it should be, maybe one should find some kind of some jet-like observables, but kind of, yeah, but the, so it's in that sense. So it's well, maybe it's better, but at least my expectation, yes, there are several scenarios which one can try to say what does it mean for theory to be approximately integral at high energies. This is the most naive one, is just, yeah, you look at all S matrix elements and they just approach kind of elastic ones. I think that's too good to be true, and that's not my expectation also from this physical intuition. The expectation is that it's dominated, basically you look at high energy scattering and it goes like too hard, so it's dominated plus many soft, and these many soft, they're produced during this zigzag configuration. So as I said, well mentioned, this Wolchid theory, it's a theory of gravity, right? So in gravitational theory, we're not surprised that at high energies there is lots of soft particle production. Actually, in high dimensional gravity, we think that the way scattering goes, it's too hard going to many soft, right? Because you just you produce a black hole, and black hole evaporates by Hawking and produce many soft quanta. So in this case, I don't see a reason why two initial hard particles would disappear. But the expectation is that one will be dominated by this kind of processes. And well, that's kind of what I mean by approximate integrability, that kind of at the level of hard ones, not much is happening.
In the studio joint QCD, where we had some numerical results, it just becomes a big mess with.
No, definitely, right. So yeah. So right, what? Yeah. So this approximate integrability, to identify it, one really should look at the kind of correctly defines the observables to look at, and it's not that just soft particles not being produced. Yes.
This one see it's a WCW model, not just a bunch of scalars and anti-symmetric representation. Do you actually see that integrability meets the nonlinearity of the WCW?
All right, exactly. So the derivation was the following, because the subtlety is that so at leading order, we just need to add a bunch of scalars in anti-symmetric representation. But so we're building theory kind of which nonlinearly realizes this one d-1 broken to iso 1 times OD-2, right? And when for high D, so these scalars, they actually transform in non-trivial representation of OD-2. So to build properly the action for these particles, which realizes this nonlinear symmetry, it implies just from kinetic terms, there are additional interactions appear which are forced by symmetries. And and then we see that the only way to cancel particle production associated with those would be to introduce also nonlinearities for the scalars themselves, and then diagrammatically one can show that the only Lagrangian, actually it was kind of fun exercise. So we basically reconstructed this again by some kind of inductive arguments. We reconstructed OD-2 model from diagrammatics, and it's uniquely fixed that way. This argument doesn't allow to fix the level, but it should be OD-2.
So the fact that the phase shift is linear with energy, it leads to some time delay also.
Yeah, so it kind of, that's what I'm implying here. The physics, and maybe I should have said that, because the physics of this e to the s phase shift is very simple, right? The physics is, that's what Drauer is referring to, that the phase shift implies that there is a time delay. And time delay, when phase shift linear in S, that's a time delay proportional to the collision energy. And actually, there is something interesting here, which maybe hints on the reason for violation of integrability. Because the way it arises in Dambugota is very simple, and you see directly at the classical level. It's something which I kind of mentioned earlier, right? So you have long string, and you have excitation on a string of energy E. Then there is a length here. So the length of this excitation is proportional to energy of the excitation. And then if you just calculate now, if you have probe excitation moving here, you get the time delay, which is proportional to this proper length. And that's exactly that, and exactly reproduces this e to the s phase shift. So the s phase shift is really kind of, it's completely classical at the level of Dambugota. So at high energies, so it gets the same time delay, but from this zigzag configuration. But now there is a big difference in two cases, because here the scattering is pure transmission. And in that picture, say, because if particles are identical, you cannot separate it. But if you say introduce two different adjoint quarks or two different kind of gluon polarizations, in that case, the scattering leads to reflections. And for instance, if adjoint quarks, they have different mass, then reflections are incompatible with integrability. So kind of at least one piece of intuition, which I have, why confining strings may kind of try to avoid integrability is coming from here, that at high energies, like scattering seems to be associated with reflections, even though the time delay is the same. And that's maybe the reason why somehow this provides abstraction to integrability.
If the time delay that you get in EUV from this picture of zigzagging is exactly the same as the
Yeah, you get the same time delay.
of 2 or something, because it's
No, it's exactly the same. Of course, if there is additional particle production there, then it will be shorter, because kind of this time delay is fixed by kind of you wait for this particle to lose all of the energy. If on the way they produce additional soft quanta, then it will turn back earlier, and the time delay, so kind of effective parameter will be smaller, which is consistent with the fact that if you look at the dispersion relations, as you know very well, right? If one looks at this S matrix, so one can kind of look at the low energy expansion and define kind of IR tension, which really the parameter which determines tension of a long string. But on the other hand, one may say, oh, kind of what we're saying, that we expect this phase shift also to infinity to have asymptotics which grows with S linearly to produce the same time delay. One can write dispersion relation, which says, well, at least for single Goldstone mode, which says that LUV squared, I guess it's always LUV. It can, yeah, I think it's larger or smaller. You can have positive no, I think it's smaller, right? Because this one is always positive, for instance, and that one can be 0. So LUV squared is always smaller than LIR squared. A difference between the two is exactly given by, it's related to total inelasticity, which physically related to the fact, in this picture at least, it's related to the fact that you lose additional energy by emitting particles as the string expands. Right, but if one ignores that effect, the two calculations produce exactly the same answer, although geometrical picture is very different. In one case, it's transmission, and in another case it's reflection. And maybe that's important for kind of this, for instance, for appearance of axion in D equal 4, because in D equal 3 we have one flavor, so there is no way to distinguish reflections from transmissions. But in D equal 4, somehow this picture suggests that starting from exact transmission, you want to go to exact reflections at high energy, and maybe that requires some kind of resonance. But